Good morning to everyone. The title of our work is Characterization of 3D printed ABS specimens under static and cyclic torsional loadings, developed by Carla Ferreira, Carlos Vicente, Manuel Sardinha, Marco Leite and Luís Reis at Instituto Superior Técnico from Universidade de Lisboa in Portugal. Scope and motivation. In the past years, several authors have dealt with the influence of printing parameters on 3D printed parts, the majority focusing on the tensile properties of these components. Some authors have also studied the properties of fused filament fabrication parts under tensile and bending cyclic loadings, but few have studied the impact of torsional cyclic loadings, leaving a gap in the literature to be fulfilled. Therefore, this work aims to broaden the understanding of torsional, monotonic, and fatigue properties of 3D printed polymeric materials. To accomplish this, the high cycle fatigue response of fused filament fabrication ABS solid cylinder specimens under static and cyclic torsional loadings is studied. Methodology. ABS from Ultimaker in the form of a green filament was selected and solid cylinder specimens were printed using Ultimaker 3 and its own slicing program Cura 4.9, shown in Figure A. Since there is no specific standard concerning the additive manufacturing of polymeric cylindrical components under monotonic torsion and cyclic loadings, the guidelines from the ASTM E14313 and ISO 18338-2015 were taken into consideration to design the test method and specimen shown in Figure 1. Specimens were printed in the upright orientation since support structures would be required if specimens were printed in the XY orientation, as shown in Figure B. Instron 8874 biaxial servohydraulic testing system was selected to perform monotonic and fatigue tests, shown in Figure A and Figure B. Monotonic torsion tests were conducted with a rate of angular displacement of 0.1 degrees per second. To study the mechanical properties of ABS specimens, a set of 6 combinations with 3 repetitions was developed, and concentric and zigzag infill patterns were assessed, varying the number of counters between 1, 2, and 3. Table 1 shows this first set with the associated number and letter coding for each case. The remaining printing parameters were kept constant and are listed in Table 2. Because an overlap between adjacent printed rasters was introduced, an infill percentage of 113 was used rather than 100. Infill was printed before walls, followed by the inner wall and so on until the last external wall was printed. From monotonic tests, shear stress strain curves, like the one shown in Figure 2, were obtained and shear modulus, shear yield strength using the 0.2% offset method, ultimate shear strength, fracture strain, resilience modulus, and toughness modulus were calculated and used as response variables to assess ABS specimens' mechanical properties. The optimized set from monotonic torsion tests was subjected to cyclic torsion loading conditions to study the fatigue performance of these components. To accomplish this, Instron 8874 biaxial servohydraulic testing system was used and it is shown in Figure A. To avoid heating, temperature was controlled with a thermographic camera FLIR A300, shown in Figure B, and Optica SZM trinocular stereo microscope, shown in Figure C, was used to evaluate specimens' fractured surface. Fully reversed, load-controlled in high-cycle fatigue regime tests were performed and 7 stress levels with only 1 repetition were chosen and assessed at room temperature with a frequency of 5 Hz. Specimens were subjected to constant amplitude loads and the corresponding reversals to failure were plotted on an Hessian curve. Fatigue properties were obtained by fitting the experimental data to the equation developed for the high cycle fatigue regime displayed on the screen. Experimental results. From the shear stress-strain curves displayed in Figure 3, it was concluded that shear modulus, shear yield strength, shear yield strain, and resilience modulus are practically not affected by the number of counters in both infill patterns. In concentric pattern, ultimate shear strength, fracture strain, and toughness modulus increase with increasing the number of walls, but the opposite occurs in the zigzag pattern, leading to a decrease in both ductility and strength. Overall, the zigzag infill pattern presents better performance than the concentric pattern. From Figure 4, it can be observed that concentric pattern tends to fracture in a 90-degree plane with specimen longitudinal axis, characterized by a ductile fracture type intorsion, and with increasing the number of counters, close to the final instant, specimen's fracture is in a 45-degree plane, showing a more brittle fracture type intorsion. Zigzag pattern also shows similar behavior, thus being characterized by crack initiation and propagation in a 90-degree plane, but in this case, there is a bigger influence of the infill pattern, resulting in a more pronounced fracture surfaces in the 45-degree plane. In both patterns, an increase of counters from 1 to 2 walls proved to be beneficial for the improvement of surface quality of the specimens, with no relevant difference between 2 and 3 walls, as can be seen in Figure 5. It can therefore be concluded that zigzag infill pattern with 1 and 2 walls proved to be the configurations with best performance under monotonic torsion loadings, with residual differences. Although one-wall configuration had slightly better mechanical properties, zigzag pattern with 2 counters was selected for the fatigue tests because it showed better surface quality. From the 7 stress levels assessed in fatigue torsion tests, the SN curve was constructed and it is shown in Figure 6 with a R² of 0.9069. From data, it was possible to estimate that the fatigue strength coefficient is 63.31 MPa and that the fatigue strength exponent is minus 0.204. It was observed that at lower stress levels, crack initiates in a 90-degree plane with specimen longitudinal axis, but also originating secondary cracks, which results in the fracture surface morphology very regular, as it can be seen in Figure 7a. When the intensity of the load is increased, specimens tend to present a flat fracture surface, as shown in Figure 7b. From factography analysis, 3 types of pores were identified. 1. Related to the physical gap between layers generated by voids, shown in Figure 8a. 1. Smaller and spherical due to entrapped gas caused by melting of filament during extrusion, presented in Figure 8b. And another type of pore due to bed fusion between deposited adjacent rasters, shown in Figure 8c. Conclusions. In this work, the fatigue response of an improved set of fused filament fabrication, ABS, solid cylinder specimens under monotonic torsion tests was evaluated. From monotonic tests, it was concluded that the zigzag infill pattern leads to better mechanical properties under torsional loadings when compared to the concentric infill pattern. Increasing the number of walls proved to be beneficial for the concentric pattern, while it reduced zigzag pattern's performance. Both pattern specimens were characterized by a ductile fracture type intorsion, with fracture occurring in a 90-degree plane with longitudinal axis, whereas zigzag pattern showed a more pronounced brittle fracture type with the helix inclined at 45 degrees with the axis, concerning the final fracture stage. From fatigue torsion tests, it was observed that the fatigue mechanism between layers governed the failure mechanism of specimens. From fractography analysis point of view, different types of voids and defects were found along specimen surface, generating stress concentrators that contributed for crack initiation. Further studies focusing on the reduction of surface roughness and improvement of surface quality, for instance, by using acetone vapor smoothing or ironing, are recommended. This work was supported by FCT through IDMEC under LAETA. The authors acknowledge the funding of the Mobile Pro U project by the Sociedade Ponto Verde and also gratefully acknowledge the funding of the Big FDM project from FCT. Here are some of the references used to support the present work. Thank you for your time and kind attention.